Okay, question 14 says temperature is a constant and the rate of change of barometric pressure P with respect to altitude H is proportional to P. So we have the rate of change of barometric pressure P with respect to height H is proportional to P. So this is exponential growth and decay. And they're saying if P equals 30 at sea level, let's go ahead actually. So we have the point 30, 0, because we have sea level is 0 feet of altitude. And then at 29 barometric pressure, we have 1,000 feet of altitude. So then they want to know what is the pressure when the altitude is 5,000 feet. So let's go ahead and write the solution to this DiffEq as P equals AE to the KT, and we can solve for A because we know that when there are, let's see, when the sea level is 0, we have 30 barometric pressure. So now I'm thinking that I wrote these points wrong, so bear with me. Well, we have time equals 0, we have barometric pressure of 30, and not when time equals 0, when altitude is 0, whoops. And then when altitude is 1,000, we have barometric pressure of 29. So that means because when height or altitude is 0, barometric pressure is 30, we have our particular solutions, well, we have the initial value of 30 right there, our A value of 30. So now we can use this other point, 1,029, to solve for K. So we put in P of 29, and we put in, instead of T, we're going to put in 1,000. I should have probably used an H there, by the way, when I integrated. So that should be an H, and that should be an H. And then I need my calculator to find out what K is. I think I'm going to do myself a favor, though, and divide by 30. So I get 29 over 30 equals e to the 1,000 K. Then I can natural log both sides of the equation. Ln here, ln here, ln of e is going to cancel. So I have the natural log of 29 over 30 equals 1,000 K. And that means that K will be natural log of 29 over 30 divided by 1,000. And bring over my calculator and do just that. Natural log of 29 divided by 30. And then divide that by 1,000. And it gets me my K value, which looks to be very small there. So K is going to be, and let me get that scientific notation out of here, 5 decimal places, so 4 zeros and a 339. 4 zeros and a 339. So now we need to plug in the height of 5,000. So I'm going to rewrite my final equation as 30e to the 0.0000339, and I'm going to put in a 5,000 there. And then let's go ahead and solve this out. We have 30 times e raised to the, I'm going to go grab that value there, times 5,000. And that gets me 25.322, which is answer choice B. All right, so then the next question is not a calculator problem. It's just giving us this slope field, and it's saying which could be the differential equation. So the way I do this is I pick an x value, and I look up and down, and I see that the x value is driving the slope, since slopes are constant at each x value. I look across at the y values, and I notice that the slopes are different at each y value. So I need a differential equation that is only dependent on x. So I got to get rid of anything that is dependent on y. And then what I need to do is find where at some positive value over here I'm going to have a slope of 0. And I can actually, I think the answer is going to be D right here, because at x equals 2, I'm going to have a slope of 0. And since we know that this value is 3 and this value is 0, that does look maybe-ish around 2. But let's take a look at each of the options. If y equals x, then anytime x is positive, the slope will be positive. I'm sorry, y prime, the derivative, the slope equals the x value. But here you see I have some negative slopes where x is positive. So the answer choice can't be A. And then a sine function, you're going to see some curvature here that we don't have. And so your answer choice is D, and this actually makes sense because when you integrate this, you're going to get a quadratic, which this appears to be.